integrate 0 to t s dw sub s and w sub s with respect to w sub s. So you have a function over here which is depending on s and w sub s. Yeah, you can say that t and w sub t, no problem at all, as dw sub s. Now in this case, because g is not only depending on w sub s but it is also depending on the s, so in that case we also need Ito Lemma, but the version will be different. So there will be another version of Ito Lemma that I will state now. So when my function is depending, let's say I have a function f which is depending on s and w sub s or t and w sub t, no problem at all. In that case, my differential looks like this: df equal to partial derivative of f with respect to s and plus 1/2 partial derivative of f with respect to, so it is going to be w second partial derivative times ds plus it is partial derivative of f with respect to w times dw, right? So because we want to calculate this integral, so we will compare, like if we integrate, then we got this f naught plus integral of f sub s here, this, okay, so this is partial derivative of f 1/2 partial derivative of f with respect to Brownian ds plus so this integral is going to be in the usual sense, like as calculus, this differential. Okay, so this is going to be 0 to t partial f with respect to dw sub st, right? So I have to compare this with this. So I need to find out a function whose differential, whose derivative, so derivative in the usual sense, like calculus 1, is equal to s times w. So s and w are variables, right? So I need such function. So you can integrate. So f can be s is constant, so it is ws squared by 2. So if we consider this function, so it is now whatever I am doing here is calculus 1 or 2, you can say that. So it is just calculate. It doesn't involve stochastic. When I'm making a case for my f on which I will apply my Ito Lemma. So my potential candidate is s over 2 times w sub s square. And now I will apply Ito Lemma on this. So I need what? I need its partial derivative with respect to s, which is going to be w sub s square by 2. I need its partial derivative with respect to w, which is going to be s times w sub s, and I also need its second partial derivative with respect to w sub s, which is going to be s simply. So now I will write my Ito Lemma again. It says that df is equal to partial derivative of f with respect to s plus 1/2 partial derivative of second partial derivative of f with respect to w squared ds plus partial derivative of f with respect to w sub s dw sub s, right? So when I insert these values, so in place of f, I will write down this function s over 2 w sub s squared, which is equal to, so partial derivative of f with respect to s is w squared by 2 plus 1/2 second partial derivative was s ds plus this is s times w sub s dw sub s. Now you apply integral from 0 to t, 0 to t, 0 to t. So this will give me t by 2 times w sub t square minus, so when you will apply the limit 0, it is going to be 0. Okay, so it is going to be 0 to t w sub s square by 2 plus s by 2 ds plus 0 to t s times w sub s dw sub s. This w is basically the Brownian, so I can rearrange to write 0 to t s times w sub s dw sub s, which is equal to 0 to t w sub s squared by 2 plus s by 2 ds plus t over 2 times w sub t square, right? So then we can do what? We can make a little bit more simplification, 0 to t s w sub s dw sub s, which is 0 to t w sub s squared by 2 ds plus 0 to t s by 2 ds plus t over 2 times w sub t square. So this is going to be 0 to t w sub s square by 2 ds plus, this is simple Riemann integral, or the integral from calculus 1, which is t square by 2 plus t by 2 times w sub t square. So I can write this even in the more better form, which is 0 to t s times w sub s dw sub s, which is equal to, so like it is going to be t square by 4 plus t over 2 times w sub t square plus 0 to t w sub s square 1 half ds. Now this integral over here is the integral of a function which is random, or which is a stochastic process with respect to a deterministic, variable. So this integral is computed, numerically with different ways, which you will see if you do numerical stochastic differentiation or integration. So in this way, so this stochastic integral is equal to this guy over here, right? So this is how, this was one technique. So this was also the technique of computing stochastic integration, which involved the Ito Lemma. Yeah, the Ito Lemma, right?